Hello guys, welcome back to another video. Now, let's talk about the normal force. What is the normal force? Well, think about it like this. You got a box sitting on a table. Now, if I just remove this here. Now, if you look at this diagram, what's wrong with the diagram? All right. Now, we have a box sitting on the table, but the thing is that the box is at rest. However, from this free body diagram, it kind of looks like this box is just going to fall through the table, right? Because there's the force of gravity that's pulling the box down, and it looks like, well, because there's a force in a downwards direction, well, then there has to be an acceleration downwards, right? Because force is equal to, or net force is equal to mass times acceleration. So if there's a force, there's an acceleration, and therefore it kind of looks like this box is just going to fall through the table and go towards the earth. That's not what happens usually in a lot of cases. The box is usually just going to be at rest when it sits on the table. Therefore, there has to be a force that counteracts the force of gravity such that the net force is equal to 0 and the box stays at rest. And that force is called the normal force. The normal force is always going to be perpendicular to the surface it's on. The object is on, so if I have the same 2 kilogram mass on a slanted slope, the normal force would be perpendicular to that. All right. And this normal force is actually what's stopping this box from just falling through the table. Because there's this force upwards that sort of matches the force of gravity, well then it's not going to fall through the table. So another way I can kind of write this is that, well, if I take my normal force, right, and I say I add this to my force of gravity, so I take my normal force, I don't need parentheses, I take the normal force and I add it to equal my force of gravity, I know that the net force has to be equal to 0, right? So these two things have to be equal to 0. Therefore, I can say that my normal force is equal to negative of the force of gravity. And this negative sign makes sense because they're in opposite directions. So think about it like the force of gravity is pointing downwards. Let's say it has a weight of 50 newtons. Therefore, the normal force has to counteract this weight by pushing up with a force of 50 newtons. All right, so these forces will just balance out and the box ain't going to be moving. It's important to kind of differentiate this from, well, something called Newton's third law. You might have remembered that Newton's third law is basically action-reaction. So one example would be, imagine if I kick a soccer ball. Now the soccer ball is going to feel a force, right? So there's going to be force that's from my foot to the soccer ball. However, at the same time, there's actually equal and opposite force from the soccer ball to my foot. That's why if I kick a ball too hard, it's going to hurt my feet, right? Because there's going to be an equal and opposite reaction force back down on your feet. It's important to understand that these forces are on different objects. So while this force right over here is from my foot to the ball, this force right over here is from the ball to my feet. So these are on two different objects. The normal force, it acts on the same object. So for this object right over here, there's going to be a weight to this object. And as a result, on the same object, there's going to be a normal force. So the forces are able to cancel out. An example of Newton's third law in the same context would be this object right over here. It's experiencing some attraction to Earth. But as a result, the Earth experiences the same but opposite attraction to the object. So you see how it's between two different things. Meanwhile, the normal force is on Apple. The normal force, most of the times, it's going to match gravity. What do I mean by matching gravity? Let's say if I have an object that's 10 kilograms. All right. Now, first of all, what is the weight of this object? Well, the weight of an object is equal to the mass multiplied by the acceleration due to gravity. The acceleration due to gravity is 9.8, and this object has a mass of 10. So 10 times 9.8 gives me 98. In this case, 98 newtons, because whenever we're dealing with forces, it's always newtons. Now, this means that the normal force, F of n, it's going to counteract gravity by having the same magnitude. All right. And let's assume that whatever surface that this block is on is strong enough to hold the block. Unless the table is like really, really weak, and then like the object just falls down because the table is weak, that would be sort of like an exception. But let's just kind of like assume that this table is strong enough to hold our block. So we don't have to worry about the table breaking. Let's say if this is my hand, and let's say if I lift this block up by 40 newtons, the normal force is actually going to change in this scenario. All right. Now, why is that? All right. Well, look, so the force of gravity is 98 newtons, meaning that in order for me to actually lift this block, I actually have to have a force that's greater than 98 newtons, so that there's actually a net force that's pointing upwards. However, in this case, with my hand, I'm only exhibiting an applied force of 40 newtons, right? So I'm still not strong enough to lift this block up. However, the thing is that I have to keep the forces equal. So my normal force is actually going to be 58 newtons, right? Because notice how 40 newtons upwards plus 50 newtons upwards, subtracted by 98 because it's going downwards. Notice how that leads me to a net force of 0. And that's exactly what we want, right? If I'm not strong enough to lift up this box, it shouldn't move at all, right? So the net forces have to be equal to 0. However, the thing about the normal force is that if you're not strong enough to lift the box, it's going to sort of adapt the normal force. Because if you apply a force to try and lift up the box, the sum of the forces still have to be equal to 0, right? In order for the object to continue staying at rest. A common type of normal force problem is when somebody's in an elevator and they're either going up or down, and given a mass, you want to calculate the acceleration. So how would you do this? Let's just say that, well, I got a dude in an elevator and he has a mass of 3 kilograms. And I want to calculate the normal force. So how do I do this? We also need an additional piece of information. And notice how when you look at this formula, there's this plus or minus here. If you're going up an elevator, think about it, you're going to feel heavier. So therefore, there's going to be a higher normal force. Meanwhile, if the elevator is going down, you're going to have a lower weight, right? So you're going to be subtracting. Think, right? Now, let's just say that my acceleration upwards is 2 meters per second. So we're accelerating upwards. Let's say the dude has a mass of 3 kilograms, and we want to find out the normal force. Now, it's important to note that in this formula right over here, the force of gravity is actually going to be a positive value. And this just comes from the fact of Newton's second law. This just says that the sum of the forces, or the net force, is equal to mass times acceleration. So I can write that the normal force plus the force of gravity is equal to mass times acceleration. All right, and if I move this to the other side, I get F of n is equal to negative F of g plus the mass times acceleration. But the thing is that, remember, gravity acts downwards, and we usually associate downwards with negative. So F of g is a negative value, but we also have a negative sign right here. They cancel out. So that's why when I'm writing out this formula, I'm kind of implying that F of g is already a positive value since we have the 2 negative values that cancel out. So just remember that when you're doing these types of problems, this value should always be positive. So we're going to have our weight. That's going to be equal to mass times acceleration, mass times the acceleration due to gravity. So 3 multiplied by 9.8. And that gives me 3 times 9.8, 29.4 newtons. All right. And then because we're going up, we add, and mass times acceleration. And I just put all this into my calculator. And let me see what I get. Should I get 35.4 newtons? I get 35.4 newtons as my answer. And that makes sense because when you're going up the elevator, you're going to feel heavier. So it makes sense that the normal force is more than this gravitational force. And likewise, if the elevator was going downwards, then instead of adding, you would just subtract, and then the resulting answer would just be 23.4 newtons. So you would feel lighter, and that also makes sense here. Another way you can write this formula actually is F of n is equal to, and the force due to gravity, you can just write that as mass times gravity, right? Plus or minus mass times acceleration. If I factor out an m here, I get F of n is equal to mass multiplied by gravity plus or minus the acceleration. So that is another way you can write out the formula in like a more concise form. Now, let's talk about the force of friction. So the force of friction, probably heard of this before. Like if you got a car driving on the road that creates friction, or if you do, have you ever done the thing where like you got 2 hands, right? and you rub the hands together like really, really fast, and it generates like heat, right? Due to friction. Friction is weird because it generates heat like that. But basically, friction is like a resistive type of force. All right. And that's due to the fact that if you have like a rug, for example, let's say you have a rug. Now, a rug is very bumpy. So because the rug is really bumpy, all of these edges are going to be like not aligned perfectly. And that's going to cause like resistance to an object's motion. All right. And that type of friction, when an object is moving and there's friction opposing it in the opposite direction, that's actually called the friction, but it's kinetic. So the object is moving. So kinetic friction. All right. However, there's actually a different type of friction, and that's static friction. And from the word static, you can infer that that occurs when an object is not moving. All right. So an object is at rest. So let's say if we have, once again, 2 kilogram box, it's on some sort of rug, but this time it isn't like moving. All right. It isn't moving. You apply a force to try to get the box moving. However, static friction in this case now, static friction is going to oppose it. Now, static friction is actually a pretty confusing concept. So let's actually dive into it. The formula for static friction is, I can just say that the static friction, this is going to be equal to a coefficient of static friction multiplied by the normal force. All right. Now, this coefficient of static friction basically just indicates how rough of an object you have. If you have like something that's smooth, like ice, there's probably not going to be that much friction. So this value would be decently low. But if it's something like a rug, once again, that's very bumpy, this coefficient would be pretty high. And it's also going to be proportional to the normal force that the object experiences. All right. So basically, the heavier an object is, because remember, a normal force is related to the force of gravity. And force of gravity is equal to mass times, the acceleration due to gravity. This is basically saying that, well, if you get an object that's pretty heavy with a high normal force, well, that means that there's probably going to be more friction. And that makes sense, right? Think about like the tires on like a car. Imagine how much friction that causes with a bumpy asphalt ground compared to like dragging a toy car across a rug, right? There would be so much more friction on that big car than that toy truck or that toy car. Now, for static friction, it's actually inaccurate to say that, well, that's kind of the formula for it. This is actually the formula for the maximum static friction. All right. Think of it like this. In order to get this 2 kilogram box to move in the first place, you need to pass some barrier of energy or some barrier of force in order to actually get the object moving. And the maximum of this static friction force represents that specific barrier you have to surpass. All right. So in this case, if my coefficient of static friction is, let's say, 0.5, and my normal force is, let's say, 100, 0.5 times 100 is equal to 50. And because this is a force, it's going to have the units newtons. All this means is that the barrier of force that I have to put in has to surpass 50 newtons, meaning that if I want this object to move, I have to pass in something like 52 newtons or 53 newtons. If I pass in something lower than that, like 40 newtons, what the force of static friction will do is it'll counteract that by also passing in 40 newtons. So if it does not reach the barrier, the maximum barrier, then it's going to just copy it. It's sort of like the normal force in a way, right? It kind of like copies or matches up with that force, with the other force. So if this would be like 30 newtons, for example, what's going to happen is this is going to kind of check the maximum static friction, and it's going to be like, oh, 50 newtons, that's the barrier I have to pass. But right now I'm only passing in 30 newtons. So what I'm going to do is I'm just going to match up with that applied force. And therefore, these two forces cancel out and the object is not going to move. So if I pass in 60 newtons, so notice how if I do a force that's greater than my barrier, then the object is actually going to start moving. And that's when static friction actually immediately changes to kinetic friction. So after once the static friction thing, it sort of realizes that the force I put in is greater than the max barrier that it has. So it's immediately going to shift to kinetic friction. And it basically has the same formula where this coefficient is just going to be different. This is the coefficient of kinetic friction. But kinetic friction, it's much simpler than static friction. There is no max kinetic friction for this. So you're going to be chilling on that part. So let's say if once again my normal force, what I put 100, let's just say it's 100. And let's say my kinetic friction is going to be equal to 0.3, my coefficient of kinetic friction. So that's going to give me a result of, it's going to give me a result, 30 newtons. All right, so there's going to be a coefficient of kinetic friction of 30 newtons acting in the opposite direction of the applied force. All right, so I know that seems confusing, but if you surpass the maximum force barrier, then instead of using the max calculations or the matching up calculations, you're actually going to immediately shift to kinetic friction. And usually for kinetic friction, this coefficient is going to be less. So you should end up with a smaller value in this case than what you would actually expect. The reason why this is when you have an object at rest, there's sort of more time for this box right over here for the fibers of this box to sort of match up or match up with the rug surface. So think about it as the rug and the box are going to be more tightly locked together when the box is at rest. So there's going to be more friction there. But when you actually start getting the box moving, now the surfaces sort of have less time to lock together. So usually what you'll find out is that the coefficient of kinetic friction is usually less than the coefficient of static friction. All right, at least in most real world examples. All right, let's say if I have some sort of ladder and this ladder is at rest, it's pinned against this wall right over here in this surface. Now, let's say if I highlight this point right over here as position A, and let's say if I have this position right over here, which is position B, what is the normal force of the ladder at position A? Well, we can see that the ladder is, of course, putting pressure on the ground, and the normal force is always going to be perpendicular to that. So this would be the normal force. The normal force would just be an arrow pointing straight up. Now, what would be the normal force on point B? Well, this part of the ladder right over here is putting sideways pressure on this wall, right? On this wall right over here, this point of the ladder is putting pressure this way up it. And once again, normal force points perpendicular to that. So you would, maybe write this down on an answer sheet. You would just kind of like draw it out where this normal force would be pointing this way. So remember, it's always perpendicular to this surface. So because we're putting pressure this way, the normal force has to act this way. Now, what about the force of friction? What does the force of friction point at point A? So which way does friction point at point A? Well, think about it like this. Normally, when you expect a ladder to slide, how does a ladder slide down? Well, in order for a ladder to slide down, you can think about it as it kind of slips, right? So it kind of like slips and then it falls down and then it's on the ground, right? That's how a ladder would sort of slip. So you can see that when ladders slip, it usually slips this way. And that means that the force of friction has to be in the opposite direction because it's an opposing force, right? It's sort of like a resisting force. So the force of friction at point A would point to the right. I know that seems counterintuitive, but it's because usually when you expect a ladder to slip, it slides the opposite way. And when you're sliding to the left, there has to be a friction force that's going to the right of it. And likewise, when you see a ladder slipping down, well, this part of the ladder right here slips downwards, right? When the ladder falls, you see the ladder slipping downwards and it just drops to the ground, right? So normally when the ladder falls, it goes down to the ground. So that means that the force of friction has to point opposite to that motion, right? It has to be pointing up in order to resist that force that's sort of carrying it down, right? So that is how you would highlight the normal and the frictional forces kind of going on this ladder. So let's get an introduction to inclined planes. Inclined planes are just when you got this object, it's sitting on some sort of slanted surface at some angle. Now let's try and come up with a proof for the normal force, because remember, the normal force is always perpendicular. So let's try to come up with a formula for the normal force and the force of gravity that's actually pulling the object downwards. All right. Usually gravity pulls objects completely straight down, but I want to find out the component of gravity that pulls it this way. Now we can start off by extending this normal force line to be sort of equal and opposite, right? So if I find out the length of this right over here, then I essentially find out the length of the normal force, right? And let's just label this line as the force of gravity in the y direction. And let's label this line right over here, this vector, as the force of gravity in the x direction. All right, so if I'm talking about the force of gravity in the y direction, that usually corresponds with the normal force. And if I talk about the force of gravity in the x direction, that corresponds to the force of gravity that actually pulls the box down. Now we can connect these two lines, right? You can think about it as we can connect the force of gravity in general with the force of gravity in the y direction, and we get the force of gravity in the x direction. right? So notice how these two lines are essentially parallel, and we also have formed a right triangle here. Now that we've formed our triangle, we can actually prove that this angle right up here is actually the same angle that's down here. Let's do a simple example. So notice how this right over here forms a right angle as well. Because remember, the force of gravity is straight down. So this would be perpendicular to this surface right over here. If this angle was, let's just say, let's work with numbers here. If this angle right over here was 30, this angle right over here is 60. All right. But the thing is that this angle right over here also has to be 90 degrees, right? Because it's perpendicular, right? I extended this line from the normal force line, which is perpendicular. So 60 plus what number gives me a 90-degree angle here? And that's going to be 30. So you can see that I proved that sort of this angle and this angle that's sitting here are going to be equal to each other. So I'll just put a theta here. Now to find out the sort of x component of this, well, I can just use sine, right? Sine of theta, sine of this angle, that's going to be equal to the side opposite of it, which is the force of gravity in the x direction, divided by the hypotenuse, which is just the force of gravity. And likewise, I can find cosine of theta. That's going to be equal to the adjacent side here, force of gravity in the y direction, divided by the hypotenuse, which is just the force of gravity. Therefore, I can derive two formulas. The force of gravity in the x direction, so the direction that actually pulls the object downwards, that's going to be equal to the force of gravity multiplied by sine of theta. Or if you've probably seen this in maybe your textbook or what the teacher says, but it's going to be equal to mg sine of theta. Because remember, force of gravity is equal to mass times gravity. So I'll just simplify to that. And the force of gravity in the y direction that corresponds to this sort of normal force, that's going to be equal to mg cosine of theta. All right, so if we define sort of the x direction to here. This is basically our new x-axis, right? So this is our new x-axis. This is where the box basically moves up and down this ramp. And our y-axis is going to be this new sort of direction. All right, it's going to be this direction that's perpendicular. You can think about it as like a normal force direction. This is our new y-axis. So I know this is weird, but kind of all we did was we rotated our coordinate plane so that the x direction is referred to as this and the y direction is referred to as that. Okay. So therefore, the main key takeaways is that the force in the x direction of gravity, that's going to be equal to mg sine of theta, and then the y component is going to be mg cosine of theta. Wait, there's actually another thing. If let's say we have a force, isn't that equal to some sort of mass times acceleration, right? Isn't that equal to some mass times acceleration, right? This is a perfectly valid statement. And this is really useful because imagine if you're trying to find out the acceleration in the x direction. You can calculate the force in the x direction, of course, but if you're trying to find out the acceleration in the x direction, so basically how fast does the box move down, well, notice how you have this equation right over here. Mg sine of theta is equal to mass times acceleration. The mass cancels out, and you get that the acceleration, that's going to be equal to g sine theta. And let's just say the acceleration in the x direction here. So notice how acceleration is not dependent on mass, meaning that you do not need to know the mass of the object in order to find out the acceleration of the object. All it's dependent on, assuming that we're on Earth, is the angle of which, this surface has. So let's actually do a practice problem. Let's say got a small block, it starts from rest, and it's inclined at 27 degrees. Now, after 1.8 seconds, how far has it traveled along the surface of the ramp? So, because the block is sort of traveling downwards, right, it's going to cover some sort of displacement, which we can call d. And we want to find out how far did it travel given, so you're trying to find out displacement, you're given the time, which is equal to 1.8 seconds. And yeah, well, the thing is that when I'm seeing this type of problem, I also know that I can calculate out the acceleration from the new formula that we just learned. So we do know that we have the potential to find out the acceleration, right? We know how to find that. What formula links together acceleration, time, distance, and also initial velocity? because we start out at rest, right? So our initial velocity is 0. What formula relates all these 4 variables together? Well, it's the what is it? v1t and then 1/2 at squared, right? This kinematic equation, this guy we want to use. Now, because our initial velocity is equal to 0, well, 0 times whatever this time is going to be 0. So effectively, our formula is just going to be 1/2 at squared. So if we find out the acceleration, we basically have displacement in the bag, right? So let's just actually do this all in one go. Let's see if this works. My displacement is going to be equal to 1/2 multiplied by my acceleration in the x direction, which is just g sine of theta. So that's just 9.8 multiplied by sine of my angle, which is 27. And then this is going to be multiplied by my time squared. So 1.8 squared. 1.8 squared. And then now this is all just going to be calculator work. Okay, I just put everything into the calculator and I got that my displacement is equal to 7.2 meters. So that is how you solve these types of problems, okay? So you can calculate out the acceleration pretty instantly, and then if you're given, sometimes you might be given the displacement and you have to solve for the time, but you should have enough sort of variables. It's especially important to note that, it's important to note this word rest, right? So that you're able to sort of cancel out the initial velocity term multiplied by time, if possible. Imagine 2 boxes on this frictionless floor, and I apply 20 newtons to these 2 boxes. All right. Now, how can I sort of measure the force of box 1 on the force on box 2? So basically, if I push box 1, right, it's going to cause everything to move. But the thing is that as things move, right, as this 2 kilogram sort of moves ahead, it's going to hit the 3 kilogram block, and it's going to exert some force on it. So I just want to find out the force block 1 exerts on block 2. Now the formula for this is actually pretty simple. So the force that block 1 exerts on block 2 is going to be equal to the acceleration, the total acceleration. All right, and I know that seems a little weird, but I will explain that. And then you're going to multiply that by mass 2. So let's actually apply this formula. So the total acceleration of the 2 boxes, you can think about it as these 2 boxes, because they're sort of conjoined together, they're still 2 different objects, but because they're moving together, you can sort of treat them as a singular object. So the total mass of this is going to be 5 kilograms. All right. And then you apply the force of 20 newtons, and then you want to find out the total acceleration. So notice how this is just force is equal to mass times acceleration, right? This is just force equals mass times acceleration, except for the fact that my mass is going to be the combined mass of these 2, and this acceleration refers to the sort of total acceleration experienced by the blocks. All right. Maybe total isn't the best word, but I guess we can say the acceleration of like the whole system. All right. So you just divide, 20 by 5, and you get that acceleration is equal to 4 meters per second squared. Now you just plug everything in, right? So 4 meters per second here. Mass 2 is 3. So 3 times 4, that's going to be equal to 12 newtons. So the force that mass 1 exerts on mass 2 is going to be equal to 12 newtons. All right. Mass 1 on mass 2 is 12 newtons. And as a result, due to Newton's third law, if block 1 exerts 12 newtons on block 2 has to exert this equal and opposite force on block 1. So the force that block 2 exerts on block 1 would also be 12 newtons, but it wouldn't be in like the opposite direction. Now, how do we make intuitive sense of this? So we know that the total acceleration of stuff is going to be 4 meters per second squared. Now let's calculate the force individually for block 1. So I guess I can say that the force just on block 1, that's going to be equal to my mass, 2 kilograms, times my acceleration, which is 4 meters per second squared. And that's going to give me a force of 8 newtons. So this is implying that, we have 20 newtons, directly on block 1, right, of 2 kilograms. We apply 20 newtons of force, but sort of the force on block 1 is only 8 newtons because some of that gets transferred to block 2, right? So some force is lost from the transfer from block 1 to block 2. All right, so that's only going to be 8 newtons. Now, how much force have we lost? Well, guess what? We've lost 12 newtons. Whoa, that's pretty cool, right? That's the answer that we got when we applied this formula right over here. Think about it like this, right? If we apply 20 newtons, but the first block only gets 8 newtons, then there has to be 12 newtons coming back from block 2 to block 1, right? Because 20 minus 12 gives me a net force of 8 on block 1. However, if there's 12 newtons on block 2 to block 1, then there has to be 12 newtons on block 1 to block 2. So that is how you think of things intuitively. You use Newton's third law, and you see that, well, 20 newtons here, well, if the block 1's only getting 8 newtons, then there has to be a difference of 12. So there's going to be 12 in both directions. Now, if we added another block to this situation, the formula would stay the same, except for the fact that when we were calculating the total acceleration, you also have to take into account the 5 kilogram block, and you also have to add block 3 to the end. This is due to the fact that when you have 3 blocks in a row, well, a force on the first block causes a force on the second block, which causes a force on the third block. So, some force is going to be sort of lost in that, scenario. So when block 1 pushes forward, not all of the force is going to go towards block 1's acceleration, right? All the other blocks are also going to be accelerating. So we know our force is 20 newtons. That's going to be equal to our total mass multiplied by the total acceleration, right? So our total mass, well, we have 10 kilograms in total. So dividing by 10 kilograms on both sides, I get that the total acceleration is equal to 2 meters per second squared. Now, so the force of 1 on 2, that's going to be equal to mass 2 plus mass 3. So 3 plus 5 is 8. Multiplied by acceleration, that's going to be equal to 16 newtons. All right. Now, let me just put all this up here. And then just put 16 here. Now, why does this answer make sense? Well, let's think about things intuitively, once again, using Newton's third law. So when our acceleration is 2 meters per second squared, we can calculate the force just on block 1. Force is equal to mass, which is 2 kilograms, multiplied by my acceleration, which is 2. So that means that overall, this force right over here is the force just on block 1 is actually just equal to 4 newtons. Which means that there has to be a counteracting force that's 16 newtons, right? There has to be 16 newtons that come back, because if you put 20 newtons in, but the force here is only 4 newtons, there has to be a counteracting force of 16 newtons. If there's 16 newtons from block 2 to block 1, there has to be 16 newtons from block 1 to block 2. So when you look at that, you get the same answer. Now, if you want to calculate the force of block 2 on block 3, so let me just change the notation here. Block 2 on block 3, well, you would still need the total acceleration. This time, you would only need the mass 3. So this would be the formula. Okay, think about it like this, right? If we want to calculate the force on mass 1 on mass 2, in this case, your force is being dispersed over the objects that are in front of it. So that includes the second mass and third mass. But if you're trying to find out the force of mass 2 on mass 3, well, the only direction that the force is going to is this final box. That's why it only includes the mass 3 in the formula, right? So that is one way to think about it, right? You only want to use the masses that are in front of your current mass. So in this case, we want the masses that are in front of the 3 kilogram mass, or my second mass, is just this one right here. So you only include mass 3. And if we apply that formula, well, mass 3 is 5 kilograms, acceleration is 2. 5 times 2 is 10 newtons. Now, why does this answer make sense? Well, let's calculate the force just on this block right over here. So if I calculate the force just on block 2, well, force is equal to mass times acceleration. So my mass is 3 kilograms, and my acceleration is, the total is 2. That's 6 newtons. So for sort of my force of block 2, well, that's going to be 6 newtons here, right? This is the force that's happening on block 2. Now, if we're pushing 16 newtons forward, but the net force is only 6 newtons, then that means that there has to be a 10 newton force coming back from block 3 to block 2, right? If you have 16 newtons pushing forward, but we calculated the net force to be 6 newtons. There has to be 10 newtons pushing back, because 16 minus 10 gives me 6. Therefore, if block 3 exerts 10 newtons on block 2 has to exert 10 newtons on block 3. So there we go. We end up with the same answer as we did up here.